My name is Sabine Hossenfelder. I'm a physicist and research fellow at the Frankfurt Institute for Advanced Studies. And I have a book that's called Existential Physics, A Scientist's Guide to Life's Biggest Questions.
Why did you pursue a career in physics?
I originally studied mathematics, not physics, because I was broadly interested in the question, how much can we describe about nature with mathematics? But mathematics is a really big field, and I couldn't make up my mind exactly what to study. And so I decided to focus on that part of mathematics that's actually good to describe nature, and that naturally led me to physics. I was generally trying to make sense of the world, and I thought that human interaction, social systems are a pretty hopeless case. There's no way I'll ever make sense of them. But simple things like particles or maybe planets and moons, I might be able to work that out. In the foundations of physics, we work with a lot of mathematics. And I know from my own experience that it's really, really hard to learn. And so I think for a lot of people out there, the journal articles that we write in the foundations of physics are just incomprehensible. But nevertheless, we're talking about topics that a lot of people are interested in. So I kind of see it as my mission to communicate all this incomprehensible mathematics from the papers to people who don't have the education to make sense of the mathematics, especially when it comes to those big questions. My book, Existential Physics, picks up all the big questions in physics that the laws of nature can teach us something about. That includes questions like whether physics has ruled out free will, how did the universe begin, how will it end, can the universe think, are there galaxies within elementary particles, all those big things.
Are spiritual ideas compatible with modern physics?
I think spiritual ideas are perfectly compatible with physics, but physicists don't really like to talk about it. I think that they believe it makes them sound less scientific, so they shy away from it. I'm not at all opposed to religious belief. I think it's just a completely different territory than science. And every once in a while, I think that scientists actually stray over into the territory that is religion, and I don't a priori have a problem with them doing it. I just wish they would be clearer about that they're actually doing religion. If you look at the history of science, then it's pretty clear that religion and science have the same roots. They both grew out of our desire to better understand the world around us, to better understand our own existence. And so a couple of 100 years ago, those two paths split up. And now we have science and we have religion, and they kind of don't really talk to each other. But science still tries to address some of those big questions, and especially in the foundations of physics.
Is my dead grandmother still alive?
I had the idea for writing this book when I was sitting in a taxi together with a young man who told me he's a DJ and he'd be playing music at some kind of literature festival. And when I told him I'm a physicist, he said, "Oh, can I ask you a question about quantum mechanics?" And I had nowhere to go, and we were stuck in this taxi for like at least an hour. And so I thought, well, okay, go ahead. And he said, a shaman told me that my grandmother is still alive because of quantum mechanics. Is this right? And I had to pause for a moment and try to understand what he was going on about. And after thinking about this for a while, I came to the conclusion it's not entirely wrong. And this made me realize that there are a lot of things, like those big existential questions about afterlife and about free will, that physics can actually tell us something about. And those are stories that we normally don't tell.
What is Einstein's concept of now?
Okay, so let's talk about the physics of dead grandmothers. The thing is, it's got nothing to do with quantum mechanics. It's actually got something to do with Einstein's theory of special relativity. It's all about the reality of time. It's all about the question whether the present moment, this now which we experience ourselves, whether this is of fundamental importance. Before Einstein, time was this universal parameter. We all shared the same moment of time, and we all had the same moment of now that we could all agree on. But then Einstein came and he said, well, it's not that simple. And the major reason for this is that the speed of light is finite, and it's the same for all observers. Oh, and also, nothing can go faster than the speed of light. And this sounds like a really innocent assumption, like all this stuff with the speed of light, but it has a truly fundamental consequence, which is fairly easy to understand, actually, if you ask yourself whether you know if the screen in front of you is actually there right now. So naively, we would say, yes, of course, it's there. I mean, I'm holding it in my hand, or I see it directly in front of me. But we just learned that the speed of light is finite and nothing can go faster than the speed of light. So everything that you experience, everything that you see it as it was a tiny little amount of time in the past. So how do you know that anything exists right now? What do you even mean by now? So this is the problem that comes up in Einstein's theory of special relativity. And Einstein tried to construct a notion of now in this new theory, and he failed. And he just came to conclude that this moment of now, which we experience, is fundamentally meaningless. Every moment is now for someone somewhere. So imagine you're looking straight ahead and there's a train going through to your line of sight, say from the left to the right. And on the train, there's your friend, and let's call her Alice. And as you probably know, in Einstein's theory, all velocities are relative. So you would say the train is moving relative to you from the left to the right, but Alice would say, well, actually, you are moving relative to her from the right to the left. Now, let's also imagine, this is theoretical physics, so there's a lot of imagining going on there, that at the exact moment that Alice, who's standing in the middle of the train, is looking straight at you, there are light flashes going off on both ends of the train. And the question is, did these light flashes happen at the same time? So this is the question you're trying to answer. Now, if you want to answer this question looking at the train, that's pretty straightforward. You can just forget about the train. There are those light flashes going off. They both come from sources that are the same distance from you. So of course you see them at the same time. You would say, yeah, sure, they happened at the same time. But how does the same thing look from Alice's perspective? So the light flashes go off, but while the light travels towards her, she's moving towards one of the light sources and away from the other. So the one path of the light is shorter and the other one is longer. So from Alice's perspective, the light flash from the front of the train arrives earlier than the one from the back. So she would say, no, they did not happen at the same time. And now the important point is that, as we said earlier, this is relativity. So neither of them is right and neither of them is wrong. They both have an equally valid perspective. And what do we conclude from this? Well, we conclude from this that there is no unambiguous notion to define what happens now. It depends on the observer. So they're both right. And if you follow this logic to its conclusion, then the outcome is that every moment could be now for someone. And that includes all moments in your past, and it also includes all moments in your future. So this impossibility to define one notion of now that we all agree on is called the relativity of simultaneity. And it's super important because it tells us that fundamentally this experience of now that we all share is meaningless.
What is the block universe?
The mathematical framework that Einstein came up with to make sense of this absence of now and the finiteness of the speed of light, even though it's the same speed for all observers and also the relativity of simultaneity, is that he combined space with time to one common entity, which is called space-time. And more specifically, if you take into account that this entire space-time exists in the same sense at this present moment, because the present moment has no fundamental significance, then it's become known as the block universe. It just sits there in one piece already in place. In the block universe, the past, the present, and the future exist in the same way. There's just no way that you can single out one particular time as special. So the past in which your grandma is still alive exists the same way as this present moment. The story about the block universe changes a little bit if you take into account quantum mechanics, which Einstein, when he developed his theory, didn't know anything about. This is because in quantum mechanics we have this peculiar process of the measurement, which brings in an amount of randomness. So in quantum mechanics, the future does not already exist because it doesn't exist until you make a measurement, but the past still exists the same way as it does in Einstein's theories.
How do the laws of nature preserve information?
There's another way to look at this idea that people who have sadly deceased do in some sense still exist. And it's because of the way that all the fundamental laws of nature that we know work. They don't destroy information. The only thing that they do is that they rearrange the matter in the universe, matter and radiation and everything that's in the universe. They just give you the rules for how to put them in different places with different velocities. But you can apply those rules forward and backward. And this means that you can, in principle, if you had a really, really good computer, you could always find out what happened earlier. So in this sense, information cannot get destroyed. It can, however, become, for practical purposes, impossible to retrieve. So if someone you knew dies, then of course we all know that you can no longer communicate with this person. And that's because the information that made up their personality, it disperses into very subtle correlations in the remains of their body, which become entangled with all the particles around them. And slowly, they spread into radiation that disperses throughout the solar system and eventually throughout the entire universe, but they can't get destroyed, with two exceptions.
What are two cases where information could get destroyed?
There are two cases that physicists have considered where information might get destroyed that have so far not been resolved. One of them is the information that falls into a black hole. We don't actually know what happens with it. And the other one is the mysterious measurement process in quantum mechanics, which is also an unresolved problem. The issue with black holes is that if something falls in, it becomes irretrievable, because everything that falls into a black hole is hidden behind the event horizon and it doesn't get back out. Now you could say, well, that's not a priori a sign that the information got destroyed. It just means that you personally can't retrieve it. But you could also say, well, if I have a book and I lock it away in a chest, then I can't retrieve it, but that doesn't mean that the information was destroyed. And that was true about black holes until the 1970s or so. But then along came Stephen Hawking, and he said, Well, you know what? Black holes don't just sit there forever. They're actually unstable because quantum effects near the black hole horizon makes the vacuum unstable, and that creates radiation, which is now called Hawking radiation, which is entirely random, and it carries away mass and energy from the black hole. And as a result of this, the black hole shrinks. And eventually it's entirely gone. And the only thing you're left with is this huge amount of Hawking radiation, which is random, so there's no information in it. And all the information about whatever made up the black hole in the first place, maybe some kind of star that collapsed or stuff that fell in later, like your book, has been entirely destroyed. But a lot of physicists, me included, I have to admit, I have questioned whether this calculation is actually correct. It has a lot of shortcomings. The most obvious one is probably that we don't have a theory for the quantum properties of space and time itself. So this is a long-standing problem in the foundations of physics, which we've known of since the 1930s or so. We somehow have to combine Einstein's theory of general relativity, which describes gravity, with the quantum theories. And this would be a theory of quantum gravity, that's what it's called, but we still don't have one. And this would, in principle, have to be taken into account in this calculation of what happens with stuff that falls into a black hole, but we can't do it because we don't have the theory. This is one of the reasons why physicists think that Hawking's calculation is probably not correct, and that ultimately information is actually conserved also in the evaporation of black holes. But the case is not entirely settled. Hawking himself, interestingly enough, changed his mind about what's going on in black holes. Originally, he thought information is destroyed, but later in his life, he became very convinced by arguments that grew out of string theory, which is one of the approaches to a theory of quantum gravity, which say that information is actually not destroyed. The other possible process in which information could actually get destroyed is the measurement process in quantum mechanics. And the reason for this is that quantum mechanics is a theory in which we can only make probabilistic predictions. And for this, we use a device, a mathematical device that's called a wave function. So we describe everything by a wave function, and from this, we deduce the probability of getting a particular outcome. So you could, for example, have a wave function that tells your particle goes to the left side of the screen with 50% probability and to the right side also with 50% probability. But then by the time you measure the particle, you know it's either left or right with 100% probability. So you have to update the wave function. It's sometimes also called the collapse or the reduction of the wave function, but it's all the same thing. And now the issue is, if the only thing you know is that you measured the particle on the left side of the screen, you can't tell what the initial wave function was. It could have been a 50-50 thing, or it could have been an 80-20, or it could have been a 5-95, and you just got very lucky. All of those possible initial states are possible. And so the information about exactly what the wave function was gets destroyed in the measurement. The problem is that we're not entirely sure that this actually describes what happens. There's a big controversy around it. Exactly what are we to make out of this measurement process? A lot of people, me included, think that this is just an approximation to what is actually going on. We're missing the ultimately correct underlying theory, and this underlying theory would actually preserve information again. But we don't know, so this is another possibility where information could actually get destroyed. But yeah, so leaving aside those two examples of black hole information and the measurement process, where we're not entirely sure what's actually going on, information seems to actually be preserved forever. But of course, we know that it becomes more and more dispersed throughout the universe. And so if someone you know dies, then you can no longer communicate with them because you yourself are a very localized being and you have no access to this very spread out information. But this is a very anthropomorphic thing. It's very tied to our own existence. And who knows what's going to happen in a billion years or something to the nature of humans. Maybe there'll be some cosmic consciousnesses which will also be spread out and this information will become accessible again. So I know it sounds crazy, but for all we know about the fundamental laws of nature, about Einstein's theories and about the way that our current theories work, it seems that our existence actually transcends the passage of time. There is something timeless about the information that makes up us and everything else in the universe. I think that's a really deep spiritual insight that we get directly from studying the foundations of physics. And I have to admit that I personally find it really hard to make intuitive sense of it. It's one way to look at the maths and say, okay, this is how it works. These are the conclusions that we draw from our observations and the mathematics that we know describes it correctly. It's another thing entirely to make sense of this in your everyday life. But as a physicist, I trust the process of knowledge discovery that comes from using the scientific method, and so I take this seriously.
Why doesn't anyone get younger?
We have this big mystery in the foundations of physics. If you take the fundamental laws of nature the way that we have discovered them so far, then they work the same way forward and backward in time. So we think that fundamentally everything is made up of small particles. And for the present purposes, you can think of those particles as little balls bouncing off each other. So you have particles coming in from two directions and they hit each other and they go out again. Now, this kind of particles bouncing off each other interaction, you can run this forward in time and backward in time. It'll look pretty much the same. You wouldn't be able to tell which direction is forward in time and backward in time. But the problem is, we think that everything around us, walls, plants, and so on and so forth, is made of those particles bouncing off each other. But we don't experience our reality as being the same forward in time and backward in time. People only get older, but not younger. Eggs break, but they don't unbreak. If we drop a pebble into water, we see the water splash out and the pebble sinks. We don't see pebbles springing back out of the water. It just doesn't happen. So where does it come from if the laws work the same forward and backward? The answer to this question is that it's not just the laws themselves that matter, but it's also how the individual particles are arranged. Some configurations are more likely than others. And over the course of time, what happens is that the configurations become increasingly more likely. Another way to say this is that entropy increases. So what we mean by this is that things become more and more disorderly over time. They break, but they don't unbreak. This just doesn't happen. This explains part of the reason for why the direction forward in time looks different than the direction backward in time, because entropy only increases in one direction of time. If we run the movie backward, and we can do this mathematically with our equation, but it won't look the same. But this really only explains half of the problem, because, okay, fine, so we've said entropy always increases, and this explains why the future is different from the past, but it brings up a new problem, because entropy can only increase if it was small to begin with. And indeed, the entropy must have been very small in the beginning of the universe, otherwise we wouldn't be here today. And why did this happen? How did this come about? We have put a name to it. It's called the past hypothesis. And it literally just says, well, the entropy in the beginning of the universe was small, but we have no idea why that is the case. So we've answered part of the puzzle, but not all of it. Our current theories just don't work if the entropy of the universe wasn't small in the beginning. There are some contributions to the entropy of the universe which we understand really badly, in particular the contribution that comes from gravity. Again, there's this big issue that we don't have a theory for the quantum properties of gravity. And that would somehow have to count towards the entropy of the early universe, but we don't know how to do this. So the way that we deal with it for practical purposes is that we just assume the entropy in the universe at the beginning was small, and then everything else works. But it's not that we have any direct evidence. There's no quantity that we can measure somehow.
Is there any way to slow down the increase of entropy?
So despite the fundamental laws of nature having this symmetry between forward in time and backward in time, we ourselves have this experience that forward in time is very different from backward in time. And this experience is what we call the error of time. And we need an explanation for it. And the most common explanation that physicists put forward for it is entropy increase. So what does the error of time and the second law of thermodynamics have to do with us aging? So at first sight, you could say, well, that's all about biology. It's all about cell processes. And there are lots of scientists who are trying really hard to slow down the process of aging. And now your physicists come and try to tell them that it's not possible. So it's certainly true that there are cell processes that determine how we age, and it's really, really complicated. And I admit that I'm totally not competent to talk about. I'm just a physicist. But ultimately, what it goes back to, where all of this comes from, is the increase in entropy. So it is possible to fend off entropy increase for some amount of time in a particular part of a system. For example, there are certain creatures, like certain types of lobsters or maybe trees, that can keep entropy increase very low for a certain amount of time on the expense of increasing entropy elsewhere. And some species are better at this than others. And maybe we'll be able to slow down aging. Maybe we'll be able to live 100,000 years or maybe 1 billion years. But eventually, entropy increase will get us. This question of why we do experience an error of time and where does it come from and is there anything we can do about it has captured the imagination of a lot of science fiction writers. The most famous example might be Isaac Asimov. In his short story, The Last Question, Isaac Asimov envisions a man asking a computer, today we might say an artificial intelligence, if there's any way to stop the entropy from increasing in the universe. And for a long time, billions of years, the answer of this computer and its more sophisticated later versions is that it has incomplete information for an answer. And at the very end, when all the stars have burned out and everything has collapsed to black holes, and there's just radiation filling the universe, and the only beings that remain are completely disembodied consciousnesses that float through the universe, the computer finishes the calculation and says, "Let there be light." So this brings up the question, is this the last word on the issue? Is this it? This is how the universe will end. Entropy will increase, and in the end, nothing basically can happen. We're all in thermal equilibrium, and nothing and no one will be alive. Well, this entire argument hinges on us understanding correctly what entropy is. And as I said earlier, we don't really understand entropy for gravity. So if we don't understand entropy for gravity, we don't actually know what's going to happen with the universe. It might be much more complicated than that. So for me, the answer is we don't really know.
Is the human soul just a delusion?
Particle physicists have collected 25 elementary particles in what's called the Standard Model of Particle Physics. And those 25 particles, for all we currently know, make up everything around us, the entire universe, including us. And so, in principle, what we are is just a big collection of elementary particles. And yes, it's a really complicated one, and no one in their right mind would try to describe a human being in terms of those elementary particles. It would be entirely useless. But for all we currently know, that's what we are. Now, a lot of people seem to be a little bit uncomfortable with this. They're wondering, isn't there something more about me? Am I not a little bit more than just those fundamental particles? Where does my sense of identity come from? Where does my consciousness come from? Whatever happened to my soul? There's nothing like a soul in the Standard Model of Particle Physics. So whatever happened to that? Well, so personally, I don't think that to describe our observations, and that includes our observations of ourselves, our experience of us thinking, requires anything more than particle physics. I don't think particle physics is of any particular use. I'm happy to leave the understanding of consciousness to neurobiologists or whatever those fields are called. I'm actually not entirely sure. So this is all well and fine, but I also don't think that we need to add anything to the fundamental laws of nature that we have collected in physics. I think it's sufficient. And a lot of people have a difficulty with that. They want there to be something else, this thing that they call the soul. And one possible route that you can take is what's called dualism, that just says, well, we have the world of physics, which is where we have all those fundamental particles and atoms and gravity and interactions and all that kind of stuff. And on the other side, we have the soul, and it just lives in an entirely non-physical realm. And this is where I reside in some sense. And this is perfectly fine. It's compatible with all we know, so long as this soul does not interact with the physical side, because once it starts interacting with it, then you can observe its effects, and we don't observe them. If we would observe them, they would have to be part of our theories in the foundations of physics. So for all we currently know from the foundations of physics, everything that isn't in the Standard Model of Particle Physics plus gravity is emergent from those particles and the forces between them. And by emergent, I just mean that in principle it can be derived from it. Or as the philosophers would say, it can be reduced to the properties of those fundamental particles. And this is something that is known under the word reductionism. It's a particular type of ontological reductionism. But of course, those properties of the fundamental particles is not the only thing that we talk about, and it's not the only thing that we want to talk about. We also talk about human beings and their behavior, but somewhat more mundanely, we also talk about things like the properties of certain materials, say, like stuff has a color. There's nothing in the Standard Model of Particle Physics that tells you what's the color of a metal or something like this. Those are all what we call emergent features. They don't exist on this underlying fundamental level of the particles, but they're properties of collective assemblies of particles that in principle we could calculate. Sometimes we can actually really calculate them in practice by way of sophisticated mathematics. In most cases we cannot. There are certainly no particle physicists who can calculate what your eye color will be if you give him the properties of all the particles in your body. But in principle, you know, it should be possible. If you had a big enough computer, you would be able to calculate it. There's no observation that we have ever made that contradicts this idea of reductionism. So on some level, you could say that, yeah, we are really just constituted of all those elementary particles, and all that we can do comes about from the interaction of those particles. Even though that might be an entirely useless description of us, it's nevertheless correct. But I think that actually we're much more than that, or if on a different level you could say we're somewhat less than that. By which I mean that what's important about us is not the particles that we are made of, it's what those particles can do. And that's what's contained in the information of how those particles are put together, that they make up a human body, someone who can walk and talk and think and write books or fly to the moon or something like this. Where does this come from? Well, it comes from the way that those atoms are arranged. And when I say, to some extent, we're actually less than those atoms, I mean that in principle, we could replace those atoms with something else, maybe certain silicon structures. And we could put them in the same configuration with the same possibilities of interaction as we have in the human body. And for all we currently know about the fundamental laws of nature, that artificially composed human should be able to walk and talk exactly the same way as you can. I actually think that this is a very hopeful message, because it means that in principle it should be possible to upload your identity, and actually not just your thinking apparatus, but your entire body, to a computer, because there's nothing that stands in the way. All this information about the configuration of the atoms in your body, well, you can formulate it in mathematics and put it onto a computer.
Are we close to solving a theory of everything?
A theory of everything in the foundations of physics is a theory that combines all the fundamental forces of nature. We currently know 4 of those forces. That's the electromagnetic force, which pretty much everyone has heard of. Then there's the strong and the weak nuclear force. The strong nuclear force holds together the particles that make up atomic nuclei, and the weak nuclear force is responsible for nuclear decay. Those are all quantum theories. And then we have gravity. This is the 4th force, and it's not a quantum theory. And this is kind of the problem. It's kind of the weird outlier. And a theory of everything would combine all those 4 forces into one coherent whole. Starting in the 1970s and 1980s, a lot of physicists became very optimistic that we're pretty close to finding a theory of everything. And string theory was one of the biggest candidates for this. And partly in response to this over-optimism, John Horgan in 1996 wrote his book, The End of Science, where he picks up several disciplines of science and tries to argue that actually we're pretty close to the end. And this possibility of there being a theory of everything eventually that'll just explain it all, and that's the end of the story, is one of them. This story about there being a theory of everything that will eventually just explain all of physics is one of the things that he writes about in his book, but he's also going on about there being no progress in biology and all this stuff about chaotic and complex systems, nothing is happening there, and so on and so forth. And I have to admit that it's a very good question to ask. You could have the perspective that there is a certain period in the history of mankind where we make those big fundamental discoveries in nature, and it's just behind us. There was also some period in the history of mankind where we mapped the surface of Earth, and it's behind us. It's not going to happen that we'll discover another continent. And it's a good question to ask. Like, is the same the case with science? Have we just discovered all the big things that there are to discover? And Horgan is not saying that we'll stop doing science or we'll stop doing research, but he's saying that there'll be no new big discoveries. We'll just add some bits and pieces to the stuff that we already have. And As someone who has worked in the foundations of physics, I have to totally disagree with him on his perspective on being close to a theory of everything. And I guess this also puts me in disagreement with a lot of my colleagues in the foundations of physics. I think we're nowhere close to such a theory. And one of the reasons is that we still don't have a theory for quantum gravity that would combine the standard model with particle physics. And yes, string theory was a contender for this. But it's fallen out of favor. It just didn't go anywhere. It's not even clear that it actually solved the problem it was meant to solve in the first place. And pretty much the same thing could be said about other approaches to quantum gravity. So this thing is still unsolved. And I also, in contrast to a lot of my colleagues, think that even if we solve this riddle, it'll not be the end of the story. It'll just bring up new things. It'll open new questions. But maybe even more importantly, we have a much bigger problem in the foundations of physics, which is the measurement process in quantum mechanics. Personally, I think that's the big crack in the foundations of physics. We don't really understand what's going on. It's created some practical problems, actually, in how we analyze experiments. Physicists are just confused about what exactly it means that we have to do this measurement update. Exactly what is a measurement? Who or what does a measurement? What does it take to do a measurement? We don't know. The theory can't answer this question. And I think that an answer is needed. John Horgan recently became interested in quantum mechanics and actually looked at it. And funnily enough, he pretty much came to the same conclusion, which is that quantum mechanics can't possibly be the last word. There's got to be something better than that. The way that I think about it is really from a strategical point of view. You need to find some kind of crack to which you can apply your tools to peer it open and let the light in. And indeed, when we find this answer, it'll lead to a lot of progress. And it's not just progress in our theoretical understanding, it's also progress by way of new technology. Because if you look at all the technological devices that we use today, they're all based on quantum mechanics. All this stuff about semiconductors and gaps in electron bands and so on, it's all quantum mechanics. So if we manage to improve this theory of quantum mechanics by eventually understanding how a measurement process works, I think this will also help us to improve our technological gadgets, and it'll have a huge impact on the entire world. So I don't think we're anywhere close to the end of science.
When will we solve the measurement problem?
I'm actually quite optimistic that we'll be able to solve the measurement problem in quantum mechanics within the next 1 to 2 decades or so, just because it falls into an area, quantum technologies and quantum computing, quantum information, quantum optics, where there is a lot of technological progress at the moment. So sooner or later, they'll just stumble over something new, something that they can't explain, and then they will call for the theorists to please explain this. And this is when a lot of progress is going to happen very suddenly.
To learn even more from the world's biggest thinkers, get Big Think Plus for your business.